Hello everyone, my name is Glenn Tompol and this is Leila and Laili. We are from Group 7 in Engineering Component Design. Next please. Here we are going to show you our product for the project in engineering component design class. The uniqueness of our product is that we are going to make a type of professional chair, a foldable chair that can be extended as a bed and then can be used as a chair also, and can be used in the medical in a medical ward as a replacement for the bed. This chair has a uniqueness that it can be extended as 180 degree, so it has no difference with the traditional bed instead. Next, here we are showing you the drawing for our product. In the upper part, we are showing you the mechanical design, the drawing design in the measuring, and then in the left side of it, we are showing you if the bed is already in 180 degree extended, and then in the lower side we are showing you if the chair is folded and then it is set into the chair. Next, here we are showing you the mechanism of making it as a chair and making it into the bed. We are at the low upper part of the chair. We are having the screw pin. The screw pin can be tightened and then loosened. When it is like tightened, the chair tend to have the position to be 90 degree, and then when it is loosened, the chair can tend to have the position of 180 degree. And at the lower part we are using this pin to be set in the hole at the side of the chair. Here at the lower part, the spin will set the lower part move freely, and then when it is used, the chair cannot move freely. Next, we have Lely.
Okay, next we have the stress analysis and safety factor calculation of the sitting position and in the horizontal position, which is in the 180 degrees, where this is the main critical part. And here we have some assumption, which is neglecting the friction force and applied load 1,500 Newton made of stainless steel austenitic family type 304. And from the Sikili books, we can obtain from the table A22, the yield strength is 276 MPa, and for the tensile strength is 568 MPa, and for the Young modulus is 180 GPa. Next, here is the free body diagram as a system of the horizontal position, which is in 180 degree position. Next, here is the first body diagram, first free body diagram, which is in the base of the design. We have 1,500 Newton, and then we can determine the reaction force, which is RBY 609.37 Newton and RAY 890.63 Newton. Next, and will be explained by Glenn.
As the support for the middle part of the chair, we have the stack hydraulic. This stack hydraulic is tend to give the force for the chair to move up and then to fold it itself to lower down the height. Here we have hydraulic 1 and hydraulic 2. Hydraulic 1 has like more smaller P allowable than the hydraulic 2. And also for the static height, we have rotary. This static height is used because the hydraulic is not having the height the satisfying height, so we use the static height here. Next will be explained by Layli again.
Okay, next is, as explained by Glenn, we use the hydraulic system as for the lifting mechanism to adjust the height. According to Pan et al. 2015, we have the allowable stress of the hydraulic system with the diameter of 25 millimeter, which is 73.55 MPa, and for the another one is 98.07 MPa. Since we already know the mass of the hydraulic, we also determine the allowable stress, which is 98.61 MPa. Next, here is the main critical part of the handling state analysis. By analyzing this handling state, we can determine the static and fatigue safety factor. And and here is the calculation. We can by determining the moment at O and the force at Y, we can determine the RH and RG. Next, after that, we can determine the moment that act on this on that free body diagram, and then we can determine the SFD and BMD. Next, from this SFD, we can determine the shear stress, which is 3.31 MPa. Next, and then for the BMD, we can obtain the maximum bending stress. It is 38.51 MPa. Next, will
So
be explained by Leila.
So in here we will analyze the stress analysis and safety factor calculation during the sitting position. So for the principal stresses, in here we know that the sigma max is equal to 38.51 MPa and the sigma minimum is equal to 0 MPa. Then the allowable shear stress, we know that it is equal to 19.26 megapascal, and for the allowable normal stress, it is equal to 138 megapascal. And for the static safety factor calculation, we use the MSS theorem to find the safety factor. In here, we got the safety factor is equal to 7.17. And in here, we'll do the fatigue analysis and safety factor calculation during sitting position, which the material already explained by Layli in the previous slide, and with the additional condition where the material is non-rotating bending and it is also machined and cold drawn. For the SE prime, it is equal to 284 megapascal. Then we need to find Ka, and we get the Ka is equal to 0.8399. Then we continue to calculate the Kb, where we need to find the DE first with the formula that's shown in the slide, and we can calculate the Kb is equal to 0.8903, and then after that we need to calculate the Kc, which is the Kc is equal to 1, and then we can calculate the endurance strength, which equals to 212.38 megapascal. And for the sigma A and sigma M, we can know by substitute the moment max and moment minimum to the equation, and we can get the sigma A is equal to 17.67 megapascal, and the sigma M it is equal to 20.86 megapascal. Therefore, the fatigue factor of safety, in here we determine it by use the Goodman criteria and ISME elliptic criteria. For the Goodman criteria, we get the fatigue factor of safety is equal to 8.3, and for the ISME elliptic criteria, we get the fatigue factor of safety is equal to 8.6. Therefore, the infinite life of this design is predicted. And
Okay,
next
for
will be explained by Glenn.
Okay, for this one, this is the analysis when the chair is extended as the sleep mode. We have the load as have the load, and then we have also the support from the downside because we have hydraulic, and we from here we have the calculation RC and RB. We have RC is negative 290 degree point 825 Newton, and RB we have 1153.3 to 5 Newton. Next, Here also we do the calculation for finding the SFD from A to B1 until from A to C1. Next, we have also the same thing here. We have the calculation until A to D2. Next, those calculation we are making the SFD here. And also for making the SFD and the MD, we use the formula that will be explained by Lela.
So in here, we use the usual formula to find the SFD and BMD. Therefore, we get the result as shown in the slide. From that result, we can conclude that from the SFD, we know that the Vmax is equal to 1584.575 Newton. So the tau is equal to 3.17 MPa. So based on the BMD result, we can calculate the sigma maximum by use the following formula that's shown in the slide. Therefore, we get the sigma max is equal to 144.5 megapascal. For the stress analysis and safety factor calculation, we know that the principal stresses is equal to sigma max is equal to 144.5 megapascal and the sigma minimum is equal to 0 megapascal. And then the allowable shear stress, we know that it is equal to 72.25 megapascal. And for the static safety factor calculation, we use MSS theorem. Therefore, we get N is equal to 1.91. For the sigma A and sigma M, we use the following formula. Therefore, we get the sigma A is equal to 63.98 megapascal and the sigma M is equal to 80.52 megapascal. Therefore, for the fatigue factor of safety, we calculate first by Goodman criteria and we get the fatigue factor of safety is equal to 2.3, and for the ISME elliptic criteria, we get the fatigue factor of safety is equal to 2.4. Therefore, in here, we know that the infinite life of this design is predicted. And for the conclusion, since the n is larger than 1, therefore our design is safe. Any addition from the others? Maybe to conclude the presentation.
I think that's all.
Okay, that's all from our group presentation, and here is the reference of this group project. Thank you for your attention and have a great day.